So you can watch this afterwards if you want. We finished the one-dimensional problems last class though with that barrier problem and the issue of tunneling. We'd seen the finite square well before that. Um, Again, there was some tunneling beyond the barriers of a finite square well. An infinite square well doesn't exist, but we also looked at that as a one-dimensional problem. If you think about it, I even gave you a wave function, didn't tell you what it was for, but the potential in that case, it turned out to be parabolic, which would be some sort of mass on a spring potential, what we call the simple harmonic oscillator potential. So we've looked at a number of these one-dimensional systems, and today it's time to maybe get real a little bit because we don't live in a one-dimensional world. Heck, we're not even flatlanders. We don't live in a two-dimensional world. Unfortunately, every quantum mechanical system that will have meaning, particularly atomic physics meaning, has three dimensions associated with it. The issue, of course, with that is the math gets a little more difficult beyond just differential equations, which is what we've been talking about with the one-dimensional system. Now we have to look at something called a partial differential equation. And so rather than having complete derivatives, total derivatives sometimes with just a derivative with respect to one variable, Schrodinger's wave equation is going to manifest itself as a sum of partial derivatives, second derivatives, right? If you think about it, but because that's what the momentum squared is, and we'll show that in just a second. But partial derivatives, which hopefully you're now experts at because you're pretty much done with your multivariable calculus class. So our odd part about this will be solving these things. And so, anybody got any questions before I get started? Because the math's going to get a little intense. Stop me at any time. The technique I'm going to show you is tried and true. It's a royal road you got to be able to travel down whenever you find yourself having to solve a partial differential equation. You solve them in this class at the very end here. Quantum mechanics class, you'll see it. If you take the advanced electricity and magnetism class, you'll run up against partial differential equations. And here's how you solve it. We're going to do Cartesian coordinates first, just because they're a little bit easier to work with. And so not hearing any questions, so I'm going to get started here. I'll share with you my iPad. All right, do the screen mirroring trick. There it goes. Okay, you can do it. All right, and hopefully you're seeing my screen here. And so we're talking about the first problem we're going to look at is a three-dimensional infinite potential well. And so we did the infinite square well in one dimension. Now we're going to make it a little more realistic. We're going to make it three-dimensional. If you're wondering what that looks like real quick, it's just a box, right? And so in the blue shaded area, that's the allowed region for the particle. Outside of that blue shaded box, the potential has gone to infinity. And so we've created a well that's three-dimensional in size, which is that rectangular box right there. And you can see in this case, we've made the dimensions L1, L2, and L3, where 1, 2, and 3 correspond to X, Y, and Z. Our author in our textbook does that. Authors, you could have made it LX, LY, LZ. It may have made it easier to remember, but keep in mind what that sequence is because it's going to come back again as I solve this problem. 1 is the length associated with X. Energy 1 is also going to be the energy associated with the X direction. It's not a component of energy, it's just the one associated with the X direction. 2 to Y and 3 to Z, and that's kind of our pattern. So that's our well that we're talking about. And so I guess the first question before we go on to solve this is, what does Schrodinger's wave equation look like in 3 dimensions? And remember, Schrodinger's wave equation is little more than a statement that total energy of a particle, even a very small particle, is equal to the sum of the kinetic energy of that particle plus the potential energy of that particle. Remember, V is not volts here. V is potential energy in joules. Okay, and very often it'll be electrostatic potential energy, like Coulomb's constant times 2 charges multiplied together divided by a distance. Okay, that same U for electrostatics that we talked about in PHY, I guess 1112 or whatever physics 2 class you took. That's what we're generally going to be talking about for systems that we look at. But it could be anything. In this case today, it's just squared off boundaries. Okay, in the x direction, it's infinite at L sub 1. It's infinite when you're less than 0, and that's what our potential is going to look like. Okay, any event. Remember, kinetic energy over and over again, hopefully, is no longer 1/2 mv squared like it was in Dr. Tech's class. It's now momentum squared over 2m. It's a little more sophisticated, but they're equivalent, and we've shown that in the past. So total energy is p squared over 2m plus potential energy. And we multiply that thing by the wave function, and we use the momentum operators that we talked about when we were using momentum operators to find expectation values, average values of momentum, which are extracted from a wave function. And you'll hopefully recall that the momentum operator is minus I h bar times the derivative with respect to x. And I hesitate there because that's the partial derivative now with respect to x. That would be the x component of momentum in 3 dimensions. Of course, by analogy, you can hopefully accept that the y component of momentum is minus I h bar times the partial derivative with respect to y. And the z component of momentum, linear momentum, is minus I h bar times the partial derivative with respect to z. And so each of these guys is going to go into their respective places because we need momentum squared. And so we're going to take each of these components, square them, add them up, and that's what's going to go right there in Schrodinger's wave equation. Well, you square a negative sign, it becomes a positive sign. But when you square an I, it becomes a negative sign. And I've factored out that negative sign from these things. And remember, I've got p squared over 2m. So that would be h bar squared over 2m, which I also factored out. And then what I'm left with is, since this is squared, that becomes a second derivative partial with respect to x, a second derivative, that's a partial derivative with respect to y, and a second derivative, that's a partial with respect to z. And so the one-dimensional Schrodinger wave equation looked like what I'm writing up here at the top, minus h bar squared over, I wish I had Sam handwriting here. Sorry, Sam. Your handwriting is just much better than mine. In one dimension, we had something that looked like this for our wave equation. My pen is doing wacky things. There it is. So kinetic energy plus potential energy is equal to total energy multiplied by a wave function. In 3 dimensions, the derivative isn't a regular derivative with the kind of block D that we use the partial derivative symbol, and there's 3 of them. And that's not a stretch. If I just told you that, you probably would have believed me. It just kind of makes sense that that would be what it is. Now, but here is a leap, and it may be notation that your multivariable calculus teacher has taught you, or it might not be, because well, didn't do what I wanted right there. I didn't want that line to go at an angle like that. It took charge. I want to take this thing and rewrite it in a way that a lazy physicist writes it, with that symbol right there, because you recognize that a second partial with respect to x on something, plus a second partial with respect to y on something, plus a second partial with respect to z on something, can be written in this shorthand with the upside down triangle squared, which we call a Laplacian. I forget what the name of that triangle is. Mathematicians give it a name. As a physicist, I don't care. This is just a shorter way of writing this in Cartesian coordinates. And I'm also hoping, because we're going to need it when we do more realistic problems than an infinite square well box, when we do spherical things like atoms that have spherical symmetry, I'm hoping that we can just transition from second partial with respect to x, second partial with respect to y, second partial with respect to z, to what the Laplacian is in spherical coordinates. And hopefully I'll get to that at the end of our little talk here today. Okay. Is there anybody that's never seen the Laplacian before? Never seen that notation? It's totally foreign to you? That is one of the risks, of course, of teaching this. If you do, just shoot me a note in chat. I'm kind of watching that, say, hey, I've never seen this. And if it isn't at least believable to you, come see me at office hours because we'll talk about Laplacians, and they're related to things that we put in this field called vector calculus, vector analysis. Laplacians, there's this thing called divergences, things called gradients, things called curls. They all use this notation with the upside down triangle. The Laplacian is the second derivative variant of that. All right, so how do we solve these things? Now that we've got that, I'm going to go back to the regular notation, not the shorthand Laplacian. I'm going to start right there. And the question then is, how do I solve this equation right here? What do I do? And in general, when you're solving a partial differential equation, the strategy is to get it into an ordinary differential equation so that you only have to do a regular differential equation, not one that has partials in it. Okay. And the technique that we use is referred to as separation of variables. Okay. And if you think about it, we use that technique. You may recognize it here in a second. When we went from the time dependent Schrodinger's wave equation, which was a differential equation, it was a partial differential equation as well, but the two variables were x and t. And what I did to get the Schrodinger time independent wave equation, the one that is more useful to solve problems, is I separated variables between time and position, separated them out to two separate equations and solved them individually. And that's the strategy here too with this separation of variables technique. Really probably don't need the initials, just separation of variables. So what's the first step of a separation of variables solution? Well, we recognize that the wave function here in Cartesian coordinates is a function of x and y and z, right? It could be x squared plus xy plus z cubed times x times y. That would be a polynomial type example that's a function of all three variables. But we don't think that would be a solution to Schrodinger's wave equation. We think that we can separate the variables out into their own individual functions. Okay. And I want to make sure I stay consistent with the book notation here with what I'm about to do. So let me make sure, because yeah, he does go that way. Okay, so my presumption here is going to be that x, capital X here, is a function only of x. I'll have another function I'll call capital Y, which is only a function of y, and then capital Z, which is only a function of z. That's the fundamental step to separating this differential equation out. Okay. If you can't do that, this is a really difficult equation to solve. In fact, maybe even impossible to solve. So that's our first equation, is that our overall solution can be separated out into a solution for x, a solution for y, and a solution for z. Okay, and so what does that mean, I guess? I'm going to rewrite Schrodinger's wave equation with a little bit of a shorthand that I'm not a big fan of, but it improves my handwriting. Psi double dot or double slash, right? That's the second derivative, but we'll say it is the partial with respect to x there. Now, you know what? I'm not going to do that. I'm not going to do that yet. We'll leave it as is. But what I will do is I'll put in for this thing right here, realizing that that's what I mean by psi. I think it would be y, which is only a function of y, times z, which is only a function of z. They're like constants with respect to the partial derivative. But then I will use this notation. Then it's that function x's second derivative. Because when I take a derivative of this thing right here, the separated solution, the only thing that varies with x is that thing. These two guys are just constants. And so I think I can write that first partial derivative just like that. And I've dropped the is a function of x is a function of x. That's why it had a second derivative. Y and z are functions respectively of the variable y and the variable z. So with respect to a partial derivative in x, they're just constants. And if you bought what I just said there, I guess the next term would be the x function and the z function as constants, and it would be the second derivative of the function y with respect to y. And then the third term, well, now x and y functions are constants with respect to the partial derivative, and we're left taking the second derivative only of the z function because that's the only thing that would have a derivative. And so we've taken care of all three of those things. And then it's conventional. Um, well, let's see. I guess I can bring the potential energy, I need a negative sign in there that I didn't write, to the other side of the equation, subtracting it off and multiplying by the wave function. So I brought that guy over to there. But let's think about an infinite square well. What are we saying is the value of the potential inside the well? Now, I don't say it right there, so I better discuss it separately. Let's see. I think in the x direction, for example, the square well looks just like the one-dimensional square well looked like. Okay, this is the x direction. I would have a similar curve for y and z, and I'm putting potential here on the vertical axis. And right here, we said that was L1 to 0. The potential energy is equal to 0. And I guess maybe it's best to call it the potential energy along the x direction. I would have a similar thing in the y direction, a similar thing in the z direction. And that's nice. Inside our well, the potential energy is 0. Outside the well, it's infinite. And so we don't have to worry about it out there. There's no chance that the particle can get outside of this box we've made here. All right, I think I'm going to do a little bit of manipulation on this equation, because once you separated out variables, as I've done here, well, I've assumed a solution that separate out variables. Now I got to take this equation and cause that to happen. And so the step we go with next is to divide by x, y, and z functions each term. Okay, so let's see what that looks like. Oh, and perhaps just to be clear and maybe consistent, I was running out of space right there. But after I brought v to the other side of the equation, psi here is x, y, z, right? That's our substitution step. So to be consistent, I had to substitute that in as well. And so dividing by x, y, and z functions do this for me. I have minus h bar squared over 2m. Those constants are always there. And let's see, I'll write it out. It's the y function times the z function times the second derivative of the x function. But then I divide through by the x function, the y function, and the z function. And of course, that cancels that cancels that, and I'm just left with the second derivative of the x function with divided by the x function itself for that particular term. I'm not going to write it out for the rest, but hopefully you can see then that the next term here would be the second derivative of the y function, again divided by all three. Two of the three cancel, and I divide that by the y function itself. And then I do the same thing to the third function. It'll be the z function's second derivative divided by the z function itself. I'm going to get rid of my one-dimensional well here because it's just there to help you visualize why I did something. And so all of that is equal to the energy, but then I divide by x, y, and z. So all that stuff goes away. So I'm done. That's what we're saying. And hopefully you can see what didn't get canceled out here was that. And so there's a symmetry to this equation that hopefully you can appreciate. All right, now here's the mathematician's theoretical step. Theoretical step. Can you, in your mind, come up with three functions, capital X, capital Y, capital Z, whose second derivatives, when divided by themselves, can possibly add up to give you a constant? Anybody got such a function? Sines, cosines, hyperbolic sines, cosines, any math function you've ever studied in your entire life that would allow that to be true? And the answer is, well, there is one, I guess. If each individual one of these terms was equal to a constant itself, well, then I could probably somehow add those constants up and have them be the total energy. Okay. That's a kind of a profound statement that I'm making without proof, but in partial differential equation world where we are right now, you have to accept it. That, mathematicians have searched literally for centuries to find three functions that would meet this bill, and they don't exist. And so, other than the constant is the one. And it could be zero, it could be some number of joules in this case, because they have to add up to be energy. Well, when I multiply by those constants out front. And so here's our presumption. We're going to say that the three constants are E1 plus E2 plus E3. Those are the three constants that the energy is equal to. And so I'm going to rewrite this minus h bar squared over 2m. And this was the second derivative of the x function with respect to x divided by itself, plus the second derivative of the y function with respect to y, okay, divided by itself, plus the second derivative of the z function with respect to z divided by itself. That has to be equal to those things. And what we're going to presume in order for that to be true is that this guy with the constants are equal to E1. And then, of course, the y, double dot, y second derivative divided by y with the constants is equal to E2. And the z second derivative divided by z with the constants, that's equal to E3. And so then we've created, out of this partial differential equation here, we've created three ordinary differential equations, and I'll just write them out just so you can see what I'm meaning here. Okay, x double dot double slash divided by x is equal to E1 minus h bar squared over 2m y double dot, the y function's second derivative divided by the y function is equal to E2. And then the last one would be minus h bar squared over 2m z second derivative divided by z would be equal to E3. And hopefully you realize if I can solve one of these, like the x function, I can solve all three. They're all exactly the same with just a slight difference. That's the subscript 1, 2, and 3, but they'll all take the same form. So let's just solve the first one, and then we'll write out the second one, hopefully by analogy. Okay. And so what do I have? I have that first one. I'll rewrite it as x double dot, double slash, really. Okay. The second derivative. That would be equal to then 2 times the mass of whatever the particle is that's trapped in this box times that energy E1 divided by h bar squared times the function x itself. And I scrolled down a little far, so hopefully you can see the algebra I worked right there. And I have made one mistake. Hopefully you see it. That negative sign, which is the bane of most physicists' existence, because we drop them all the time, like I just did right there. Well, I'd forgotten it, so there it is. Got it back in where it belongs. And we're just going to group all of these things right here, okay, less the negative sign, we're going to say that's minus k, do I call it one or x? What do I want to, k1, okay, again, one is associated with uh, the x, and that's going to be squared because that may be familiar with what we did for the one-dimensional square wave, okay, and that's my differential equation. And I have three of those. I have a similar one for y double prime, a similar one for z double prime. And the good news is we've solved this one several times. And so I think I told you last time, the answer to this differential equation, when there's a negative sign right there, could either be a complex exponential or sines and cosines. We're going to go with sines and cosines here. Something like a times the sine of k1x plus b times the cosine of k1x. And I think in exactly the same with exactly the same logic as I used for the one-dimensional square. Well, remember that that wave function here, at least this portion of it, okay, at x equal to 0, well, it has to be equal to 0 to match the wave function outside our square box where there is no possibility that a particle can be. So the wave function must be 0. Well, the problem, of course, is if the wave function has to be 0 at x equal to 0, the cosine of 0 is 1, not 0. And that means this term right here goes away. Mathematically, the way it goes away is that coefficient b is assigned the value 0. So our answer for the x function is a constant times the sine of k1 times x. And now let's make sure we know what k1 means. K1 here would be the square root of 2m, that separation energy, E1, that we had right there, over h bar squared. And we've worked with that enough times that h bar squared is under the radical. I notice a lot of you like to take the square root of it and only have the square root sign over the numerator. Perfectly fine, okay? But we've solved for the x equation. Without doing it again, hopefully you realize that the y function would be equal to some constant. Now, I don't need another constant because remember, I'm going to multiply these three functions together once I'm done, but I'll put it here. I've already used b. Let's use c now. And
Professor,
yeah, go ahead.
for the x function earlier on, why is the cos becoming 0?
Why does the cosine become 0? Remember, and I'll go back to the x direction here. It's a three-dimensional box, so you got three of these going on, right? This is x equal to 0. This is x equal to what we call L sub 1. It's an infinite well. There is no possibility, zero probability that the particle could be out there. There's zero probability that the particle could be out there. And remember, the probability is the wave function squared. So that must mean out here the wave function is 0, and out here the wave function is 0. One of the criteria we set about wave functions is that they have to match everywhere. You can't have a wave function inside the box that looks like that if outside the box it's 0. We don't allow discontinuous wave functions. And so that means since the cosine of 0 is not 0, it cannot be the solution in the x direction. And the same thing's true in the y and the z direction. Does that answer your question?
Yeah, definitely.
Yeah, okay. And so I'm going to do the same. And truthfully, if I'd have just told you sine, you'd probably go, yeah, sine works, right? Cosine works too. It just doesn't meet the boundary condition that the wave function be 0 at x equal to 0 and x equal to L. So we're going to go with sine. Y is going to be also only the sine. We'll throw out the cosine term, but now it's a different wave number. And of course, it's y right there. And K2 is going to be, and scroll up to the differential equations I have right there, it'll look pretty much the same, except now I've got that other constant right there, the 2 one, okay, the 2 constant. And so K2 is going to be square root of 2 times the mass. It's the same particle, so it's the same mass everywhere. And energy that's associated with the y function divided by h bar squared. And again, z is going to be equal to the next constant up, let's call it d, and then sine of k3 times z. And k3, giving myself just enough room here, I guess, to squeeze that in. No, not that thing. Come on, I hit the wrong button. Sorry. K3 will be equal to the square root of 2 times the mass times E3 over h bar squared. And remember what these energies are. I needed mathematically a number of constants that all add up to the total energy of the particle. They're not components of the energy, because energy is a scalar. It doesn't have components. Maybe it's partitioned energy out of the total energy. Some is associated with the x direction, some is associated with the y direction, some is associated with the z direction, and that's what those constants are. And I think that's important, because if we're to look then at the total energy, let's see. I have to look at the other side of each of the boxes and figure out what K also is. And it's using the same argument that Prince just asked about. Okay, at x equal to L1, for example, right here, the wave function also has to go to 0, because the probability outside of L1 on the positive x side is also 0. How do we make that happen? And the answer is, well, K1 times L1 has to be equal to an integer multiple of pi. And I'm going to call that integer N1, because you might guess in the y direction and in the z direction, you're also going to have an integer as well, N2 and N3. Okay, and so that means that K1 is equal to, let's see, N1 times pi over L1. At the same time, it's equal to the square root of twice the mass of the particle times the energy of the particle divided by h bar squared. Those two things have to be equal. One, because it just came out of Schrodinger's wave equation. And the second thing over here on the left, because it allowed us to meet the boundary condition that there's no chance the particle can be outside the well. So at x equal to L1, the wave function must be 0. And the only way to do that is if how to get the sign of anything to be equal to 0. Well, anything, K1 times L1, has to be equal to an integer multiple of pi. Okay, so now we're ready for my next slide here, I guess. These are the things we've decided. There's our Schrodinger's separated solution right there at the very top. There's Schrodinger's wave equation in 3 dimensions. This was what I got for the x function when I separated variables. There's a similar equation for y, a similar equation for z. There's the solution for the x function, okay? I dropped the constant, put it right in there. But look, when I find this and put it right in there, and I found the similar solution for y and a similar solution for z, when I put them all back together by multiplying them up, I've heard this referred to as you stitch the solution of the individual variables back to the total solution for the partial differential equation. I only need one constant. So if you notice, I dropped the other two, the c and the d, and we'll just keep the a constant that came from one. It's really 3 different constants multiplied together right now, but there's our wave function in all 3 directions. And I'll give you some pictures of what those look like in a second. But keep going. Whenever we have a wave function, we have to have an energy associated with that wave function in quantum mechanics, right? So if I go back to what I just mentioned right here, where I equated these two guys, let's solve for E1. Well, you square the N1, you square the pi, you square the L1 in the denominator, okay? You multiply through by h bar and you divide by 2m. And what you find is that the energy associated with the x direction is that thing right there. And hopefully it wouldn't surprise you if I said, well, the energy associated with the y direction, which I'll say is called E2, would be a different index, N2 squared times pi squared times h bar squared over 2m, but not the length of the box in the x direction, but the length of the box in the y direction squared. And it shouldn't perhaps surprise you that the energy associated with the z separated solution, okay, is going to be equal to n3 squared times pi squared times h bar squared over 2 mass dimension of the box in the z direction squared. And it shouldn't surprise you even further, I think, that since we had said that E1 plus E2 plus E3 has to be the total energy of the particle, I can add these three things up, and that must be my total energy for the particular state. And now I have three indices that define that state, N1, N2, and N3. We refer to those because we're solving a quantum mechanics problem as quantum numbers. There's three of them that define a state. And remember, K1, K2, and K3 are all related to those lengths and quantum numbers. Okay. And so there's a picture of what the wave function looks like, hopefully, that you can have. And I'll show you some here in a second. We'll start with two-dimensional pictures and then ramp up to three-dimensional pictures. And each one of those states has a particular energy associated with it. Okay. And so that's it. Now, you can perhaps see that if L1 and L2 and L3 were exactly the same, well, those things right there would be exactly the same. You can factor out that thing then, and there might be more than one set of quantum numbers, these indices, that would give me exactly the same energy. For example, if the three sides were equal in length, and let's say I looked at the 1, 1, 2 state, and then I looked at its buddy, the 1, 2, 1 state, and I looked at its buddy, 2, 1, 1. So basically, I'm saying 1, 1, 2, and 1, 2, 1, and I give myself a little more room to write here. And the 2, 1, 1 set of quantum numbers, if all the lengths were the same, well, I think all three of those states, which are unique, they have different form if you graph them in 3 dimensions, but they would all have exactly the same energy, wouldn't they? Because it doesn't matter whether you square the 2 when it's in the N1 position, you square the 2 when it's in the N2 position, you square the 2 when it's in the N3 position. That sum right there would be the same for each of these three unique states. When that happens, we say that we have a degeneracy. Okay. A quantum state is degenerate when there is more than one wave function for a given energy. In this case, there's three different wave functions: the one where the quantum number is 1, 1, 2, the one where it's 1, 2, 1, the one where it's 2, 1, 1. All three of those states, which are different, we'll graph some of the differences here in a second, but they all have the same energy. We say the state is degenerate. I don't know why we picked that word. Wouldn't have been my word of choice, but it is the one we got. Okay. Now, so let's see if we can picture what these things look like. Oh, by the way, degeneracy, of course, came from the symmetry of this problem, right? In order to get a degenerate state, I had to take this infinite square well, which was just a rectangular box in 3 dimensions, and I had to make it into a cube. I had to give it symmetry in all 3 directions, and then I introduced a degeneracy. Often, how you break a degeneracy, if you're trying to separate these states out to see them individually, is you put some sort of perturbation on one of the dimensions, and then it will look different from the other two, and you'll have resolved the degeneracy, is what we say. All right, let's look at some of these states, though. I think that's what I got queued up next. Let's think about a two-dimensional well for just a second. Ignore the third direction, the z direction, and maybe it looks like I don't know, you got a fence around your particle now and it can't get outside the fence. Okay, infinite though in the potential, there's no probability that it could be outside that kind of turquoise area on the xy plane here. So I want to graph what these wave functions look like. Hopefully there's no surprise to you that that would be the total energy. Okay, and if you tried to plot it and this thing was a square as opposed to a rectangle, there's a degeneracy right there. There's a degeneracy right there, where the order of the indices still gets you the same energy. And so we've got some degeneracies there. Okay, 1, 1 and 2, 2 are the same. Notice there is no zero in the infinite square well, because that would mean the wave function is zero, and that would basically mean there was no probability of a particle. The particle isn't in the box. That's what n equals zero is. So we just throw that out. Start the indices at 1, 1. Okay, so what do they look like? What does 1, 1 look like, for example? Oh, come on, wrong device. I think it looks like that. And if you think about a one-dimensional wave function, let's see, along the x direction, don't I just have this function right here? And don't I also have that same function along the y direction? And so we would say that the quantum numbers here are 1 and 1. And that's what it looks like. All right, hopefully you're starting to think, all right, what would 2, 1 look like? What would 2, 2 look like? Things like that. And so I do have a poll set up here. So let me get to it. And I'll ask you, here's my next picture. What are the quantum numbers for this state right here? Look at which direction is the x. And I've given you the clue here, hopefully, is take a look at the one-dimensional case and just separate it out. Are you seeing the poll pop up? Yep, somebody is. Okay. I don't agree with you. Sorry, whoever you are who just entered it. Look along the x direction and see which of these, and look, there's a number 1, a number 2, a number 3, and decide which is which along which direction. Got to vote here. I got a couple of these. So if you don't get this one right, that's all right. Hopefully by the time we're done. All right, 3, I got 7 of 8 in. All right, I'm going to cut it off. Yep, 8 or 8, 8 of 8 are in. All right, I'm going to end it and share it with you. And I think, let's see if I can draw these things. Okay, first of all, which is the x direction? Right there, right? And so look at what the function looks like. That's a bad color, putting red on red. Let's go for something that should be visible. If you look along the x direction, it looks like that, right? I think it looks just like a sine wave along the x direction. So I think n1 here is going to be equal to 2, because it looks like the 2 function here. Now let's look along the y direction. It just looks like that. So along the y direction, I think I have 1 over here. So I think n2 is equal to 1. I think the quantum number then has to be 2, 1. And so the 3 of you that picked that one right there, I think you got it. All right, let's look at some more pictures. Let's look at some more pictures. How about this one right here? And this is neat because this was done in Mathematica. I didn't, actually both of them were done. You can see at the bottom, they show you like a contour plot. So you can see what's going on there. So I'm going to stop sharing that, go on to the next one. First 3 people in got it. You're seeing it now, hopefully. 4, yep, everybody's there. I don't disagree with yes, this is kind of partitioning degrees of freedom in an energy problem. I absolutely agree with that. All right, I got one more person needs to vote here. All right, we got to get moving here. Ending the poll because I had a problem to do, and I only have a couple minutes to do it. I'm gonna share the results with you, and yeah, it is 2-2, right? I have a sine wave across the x direction. I can try and sketch that maybe. All right, I got a sine wave right here. So that looks like that thing. So that's a 2 in that direction. And if I go this way, I also have a sine wave. That looks like a 2, 2, and 2. That's not what I want to write. 2 and 2. All right, 2 and 2. So that's the answer for that one. Here's the next one. Yeah, let's start doing some counting here. It's symmetric. So the two indices are going to be the same. Is it 1, 1, 2, 2, 3, 3, or 4, 4? Or 5, 5? Yeah. All right. We're still waiting on somebody. Maybe the internet's bad. We're going to share it with you. And the answer is 4, 4. Okay. And I think I didn't draw it on my little key here that helps you with the one-dimensional case to see the analogy. But um, 2 up, 1 down is 3. You've got 2 up, 2 down here in both directions. That's actually 4. So it is 4, 4. All right. Perhaps an easier way to see that it's 4, 4, though, is to think about what we do with a wave function. We square it, right? And if you square it, it becomes positive everywhere. So even the things that were troughs become peaks again. And hopefully you can see 1, 1, 2, 1, because X is one direction. Pay attention to where the X direction is. Okay. Y is the other direction. 2, 1, 3, 1. Okay. 2, 2. If you square it, you just literally count the peaks along that direction, don't you? And of course, in the 2-2 position right here, if you're in that mode, the most probable place to find the particle. Wow, what just went on there? Most probable. Oh, I don't want that. Go away. Go away. Go away. All right, virtual keyboard just popped up on me. I have no idea why. There we go. We'll come back to it. All right, good. And now we got to move it. Any event, if you look for where the most probable place to find the particle in here in the 2-2 mode, it's right there, right there, right there, and right there, right? Those are the places you're most likely to find the particle. The issue, of course, is in order to find that probability, you're going to have to do a double integral. You're going to have to integrate over dx and dy, okay? And to find a probability. It's what you got to do, but that's why you take multivariable calculus, I guess. All right. Hopefully that makes sense. We're kind of now we've transitioned from what does the wave function look like to what does the probability density look like. And yes, in case you're wondering, once you've got this wave function, you would have to normalize it also by doing a double integral, integrating over dx and dy. Doesn't the math sound like fun? Here's some pictures somebody made. Kind of cool. You can see that bottom one there, 5, 5, right? All right, now let's transition over to the three-dimensional square well because my time is running out here. And hopefully the two-dimensional well, the corral I talked about, will allow you to see what is the quantum state here. And basically, what I've done when I've drawn these spheres is I've said, well, okay, what is the probability that it's near the middle there? And maybe you go down to 50% on either side, and hopefully you can see what the state is. Look first along the x direction, and it looks like I got two probable positions along the x direction. So that would be nx or n1 equal to 2. Along the y direction, I also have 2. Okay, so that's ny, or n2 is equal to 2. But then in the z direction, I only have one probable position. And so I think it's 1. So this quantum state would be 2, 2, 1, hopefully. And you can see that. All right. Here's one for you guys. Let me move on to, and I'm 1 minute over, but hopefully you'll grant me just a second here. What's the quantum state for this guy? And I don't know why we drew it twice with bigger probabilities. Maybe in the first one, we're only within 20% of the most probable position. In the second one, we're within 60% of the most probable position. So the three-dimensional shape gets bigger that would encompass a greater probability of finding a particle there. So what do you think this one? Look at X, look at Y, look at Z. First couple people in got it. So you're seeing the pattern here. All right. Everybody's in, and I agree with the majority here. It is the first one, right? Because along the X direction, there is one most probable position. So basically, we're seeing a shape like that in the X direction. Along the Y direction, we're seeing two most probable positions. So we're seeing that. And of course, along the Z direction, we're seeing three most probable positions. So it looks like that. 1, 2, 3 are your quantum numbers here. All right. I think I'm just about at the end. Oh, there's a couple more. What's this last one look like to you? The one down in the corner here. And I don't have a polling question. But hopefully you can see 1, 2, 3, 4, 5. Wouldn't that be 5, 5, 5 in that case? And so you can see there it's a cube, and there's a whole bunch of places where the particle is most probably going to be found in this case. All right, that's my well. Want to transition over here to the worksheet, because this is what you got to do for Friday since I didn't get through it. We haven't talked about, where am I here? There we go. I haven't talked at all about the energy, and that's what's left. Okay, so we've got a box, and remember we said we have an energy equation that looks, I can't stand that color, an energy equation that looks like E is equal to, let's see, pi squared, h bar squared, that's a lousy looking pi, over 2m times n1 squared over length 1 squared. Now, here in this problem, it's called x, but that's L1, plus n2 squared over L2 squared, plus n3 squared over L3 squared. And so what I'm asking you to do is, for these modes right here, which we've just kind of drawn pictures, so hopefully you have a picture of what they mean. I don't know why I rewrote it. It's right there. Calculate what the energy is. Tell me which ones are degenerate, and then just draw a quick sketch with balls, basically, of those particular modes. And that's what we're doing for Friday. And unfortunately, we got to move on because we're going to do a spherical coordinate issue with the Laplacian and spherical coordinates on Friday, and we're running out of days here. So this one is one you have to do before Friday's class and upload for me. Any questions? Sorry about going way over. This is the time of a course like this where it's hard to do one problem in 50 minutes, and that's what makes upper level physics sometimes a challenge in the classroom. All right, stop sharing that. Everybody good with what they got to do? It shouldn't take long. By the way, sometimes it's quicker to do this in Excel, right? Just type in the numbers and let Excel bang it out for you, as opposed to do it on a calculator. How many times you had to do? 1, 2, 3, 4, 5, 6, 7, 8 times, and then you'll immediately see the degeneracies. Hopefully, the states that have the same energy. All right. Any other questions? All right. We'll see you on Friday. Keeps you busy here, and that's about it. We'll talk about a real problem, the hydrogen atom, on Friday.
Thank you.
You
Have a
bet.
good day.
You too.